Hello everyone, my name is Marianne. Today I would like to share with you the final project of our group. It's called Marianne and it's a search engine. The members of our group are Sheng Zhuoran, Zheng Zekai, and me. Well, a search engine can be used to retrieve a variety of information on the web. This concept should be familiar to everyone. Well, Google, Bing, and Baidu are all popular for search engines. In fact, search engine is a comprehensive project. The complexity and construction difficulty of the system are relatively high, involving database, knowledge graph, distributed large-scale cluster scheduling, and other issues. The emergence of ChatGPT and other new technologies provides a possible development direction for modern search engines. The following example is a search engine built on ChatGPT, which named You. Well, it greatly improves users' experience. Well, recently, Microsoft also announced that it will use ChatGPT or GPT-4 to improve Bing search inquiries and send more meaningful content to users. So, how do search engines work? We can break it down into 3 steps. The first part is crawler, collecting all kinds of information on the website. The key points here include how to extract links, how to choose the appropriate crawl content, and so on. The second part is the analyze task. In this process, we usually build index for its need, completely feature extraction and vectorization, and identify its meaning and context, no matter it is picture, voice, or text. Well, finally, search is based on user input. This process will be based on the user-provided material to analyze, and then with the existing content in the database to check the similarity. There may be some more complex details, but we will not continue to explore. The usual process is for user to enter some text and get feedback. Well, we focus on the construction of implements of search engines. The problem to be solved are mainly divided into 2 categories. One is search. Text and image are constructive data. How to conduct targeted retrieval and make the result as close as possible to the user's expected results. For text, there are some common keyword retrieval techniques, and then, like an image, extract some color, some shape instructions, some of that feature, including its image, and then compute some value to do that test. There are some further approaches in the area of machine learning or cloning, including the transformer model, which has become popular in recent years that can take advantage of the processing of unstructured data. The other is detection, considering that the information on the internet is very complex. The main task of detection model is how to help users screen invalid information and find valuable content. Common tasks include content grading and dynamic ranking, as well as spam detection. Well, we pick spam detection as a basic task and introduce some machine learning model building and running techniques. To summarize, Marina is lightweight search engine built from scratch using Python to implement keyword-based text search and content-based image retrieval, while we also try to apply machine learning methods to identity and tag web pages with potential marketing content. Next, let's start with text search and see how Marina builds the search engine. First, do a text search. Crawl content from the website and find out all the information that user cares about. You can see here a network diagram of how everything is connected on the internet. And it's easy to see that there is all kinds of complex information. We need to gather good information, analyze it well, and find a good way to deliver the results that the user expects. The figure below shows some of the results of GitHub search in Marina. We can see the title as well as links with a basic description of the site and hints as to whether the site is full of advertising marketing or a normal web page. Here we're going to talk about how does the basic workflow of text search work. First of all, we will use crawler to do some crawling work. There is no date in the database at the beginning, so user need to submit the target website. This workflow actually has an advantage. For example, if a user wants to deploy a privacy search engine, he can use this feature to submit sites that needs to be collected and organized. The crawl record will mainly contain the website title, description, link, and other content. The crawl record will mainly contain the website title, description, link, and other content. Next, the data obtained by crawling will be analyzed. The final result will be stored in the database. Here we will introduce the text clarification technology to analyze whether the website is full of advertisements or other junk information. The technical details of this section will be covered later. Finally, according to the user query to retrieval the database and return the query results, we use a common keyword retrieval technique for text, but it is not as simple as the code in the feature. We need to consider the priority of content retrieval and some special cases.
Okay, it's my turn. Part 2. Another function we want to implement is photo retrieval, which is to search for photos using photos. We use an open datasite, which of course was obtained using the crawler tool we learned about this semester. In fact, the datasite does not directly show us the images, but a text document in the form of vibes and tags. What do we got? So our first job in this section is to bench scroll the images and store those images and the associated text information locally. The final size of our local dataset is about 1.5 GB. The number of images and keywords is about 25,000, and the number of other tags is about 1 million. Here we also save some text information for reasons that will be explained later. Based on this dataset, we used the feature engineering and similarity detection method to achieve photo research, which is a common method in the current image search engineering field. In addition to this, a simple segmentation of the photo is performed in order to extract features of different parts of the photo in a more targeted way. The figures show the common segmentation approach, which assumes that the subject of the photo will be located in the middle. Therefore, the image is divided into 5 parts: top left, top right, and bottom left and bottom right, and middle. Of course, the drawback of this approach is obvious. Not necessarily all image subjects are located in the middle part. And next, firstly, the feature engineering part will be introduced. The main task of this model is to extract the basic features of an image. There are many classical and advanced algorithms to implement this method, which will not be shown here specifically. It's important to mention that we have a simple implementation of many of these classical methods. It's a simple implication of those basic algorithms based on Python, rely mainly on NumPy, OpenCV, and Flask. Sophisticated structures like GNN or transformer are not used here. If there is enough time and effort, we will try to optimize this part further. Of course, this is part of our future work. However, we take a closer look at several popular algorithms and their principles, including 3D HSV histogram, color moments, gray matrix, D-hash, HU moments, and so on. They extract photo features based on 3 general aspects: color, texture, and shape. We focus on 3D HSV histogram and color moments in this video. The former is more in line with our intuitive perspective of analyzing an image, and later is our hard-coded implementation of the algorithm. Firstly, let's look at the meaning of each letter in HSV. In a polar coordinate system, a function is created which corresponds each angle to a color, so that we got a color plenty. H takes values in the range of 0 to 360. For example, H0 is red, H120 is green, and H214 is blue. And for S, the saturation in the HSV model refers to the purity of this light. For a painter's point of view, the smaller the eyes, the more right pigment we added. V or value refers to the brightness of the light. From the same point of view, the smaller the V, the more black pigment we added. There is another picture characterization method that is quite similar to HSV. That's HLB. We won't show you here. There is a mathematical conversion relationship between them. Both are widely available, but it is controversial which of them is more applicable to human user interface. Next, we introduce color moments, a feature extraction method related to matrix, which can effectively represent the color distribution of an image in RGB, red, green, and blue color space. We focus on the color content of each pixel block and calculate their mean, variance, and skewness. So color moments ends up with a 9-dimensional vector. The 3 colors and their corresponding mean, variance, and skewness. After understanding the features of the images, our next step is to perform the similarity comparison. By the previous step, we have extracted the features of the pictures into some sequence or distributions. The computer cannot recognize whether the pictures are similar or not, like the eyes, but it can recognize whether 2 distributions are similar or not. For the algorithm design, what we need to implement is actually the distance calculation, which calculates the distance between the qualified features of 2 images. Similarly, we list the tried method, or Euclidean distance, Manhattan distance, Hamming distance, and chi-square distance, and so on. The first 3 and the last one are very familiar method for us. Oscillating distance represents the true distance between 2 points in m-dimensional space. Manhattan distance is the sum of the x of the 2 distributions after normalization. Hamming distance represents the number of elements that need to be replaced to unify the 2 distributions, and the chi-square distance represents the difference between the statistical distribution and the simple observations. They all have a common feature that the smaller the distance, the greater the similarity between the 2 images. Here we show some results of our work. There are color moments plus chi-square distance. As seen in the first example, both the search results and the original images show a darker environment. From the second example, we can see that the feature of the coexistence of mountain and water is preserved. In conclusion, our algorithm achieves at least 2 things. Firstly, it's able to find the image itself from the database, and secondly, the search results are roughly similar in color features. Those 2 results were randomly selected by us, and we would like to mention that the majority of the search results meet our expectation. So we consider this part of the feature implementation to be relevantly successful. Of course, this result is related to our database. If we get a dataset with a large number of classified images, there may be a more detailed adjustments of our specific processing steps, which may also be part of our future work. In this part of our work, we have carried out certain diversions. For example, the keyword search image. Although it's already a relevantly major feature of major browsers, we still wonder if we could do this function, make this function initially from a simple perspective. Another information previously mentioned in our dataset is that there are also a large number of tags, keywords, and other text information. Text matching is a relevantly easy feature to implement. We roughly match the searched text with those keywords, and then display the images in the dataset that correspond to the keyword. On top of that, it might be possible to make our Marianne even better if a text-image matching features is added to this search. The next core feature we want to implement is spam detection. It's part 3. This is what we plan to implement in the future work of our last presentation. Our dataset is the classic SMS messages dataset, contain about 5,000 English messages, which are divided into two categories labeled spam and harm. And the biggest advantage for us to use this dataset is that it's easy to assess and categorize clearly enough. It's reasonable for us to use this as a data sample, considering the generality of the language expression. For this stage of our work, it's not very realistic to implement this for 100% of this function. So our main task is to familiarize ourselves with the general process needed to implement this function at the data science level. If possible, in the future, we will select newer datasets that are more relevant to the usage scenario, as people's language habits will continue to change with the time. The next step is to start describing our spam detect feature in detail. First of all, we show our dataset here, and these two crowd clothes show high frequency words. You can see that you, it, okay, will. These words appear frequently in no spam words, which is in line with our language habits. Predictably, words such as free, call, mobile phone number appear frequently in spam messaging, which is also in line with our knowledge of advertising messages. Next, we introduce the structure of our algorithm as we planned in the previous presentation. In order to achieve this classification task, we used a random forest with, uh, with supervised learning. Textual data places a higher demand on explanation. So we chose such a simple approach. The main goal is to work on showing the impact of other features we capture on the model. Another advantage of this random forest is that it has relevantly few parameters to match the size of our dataset and facilitates later turning optimization. If you have the need to explore the impact of textual content on the model and provide something more explainable, you can try some new approaches based on transformer or the like. Methods such as shape values or S or slim might also provide better explanation. Before the specific processing, we clean and split the text dataset. The text cleaning was done with an LP, and we won't show the specific details as before. After doing the normalization, removing case difference and the effect of going out to punctuation, the final result is shown as follows. And next, my team member Shang Zhuoran will introduce you something about the features engineering for this part and more about our work, Marianne.
Hello everyone, I'm Shang Zhuoran. I'm also the owner and main developer of Marianne. My partner has just given you an introduction to spam text classification task. We selected the SMS spam collection dataset and draw word clouds to see if there were linguistic features. We used NLP to process the text, cleaning, splitting the words, extracting vectors, and finally training the random forest model to complete the classification prediction. In this section, I will try to explain why the model is feasible and how to improve its performance using simple and effective measures. This will cover the feature engineering, explainability, and hyperparameter tuning. First, let's look at the feature engineering. The aim of feature engineering is to max the extraction of valuable features from raw data for using in models or algorithms. The data and features determine the upper limit of machine learning, while the models and algorithms only approximate this upper limit. The word vector is naturally an important feature of the text data. We use the TF-IDF vectorizer to transform the original context into a feature matrix. What else should we look for besides the text? Consider some statistical features, such as the length of the text, the number of punctuations, the number of numbers, and whether or not it contains links to the website. Based on these considerations, we have made some graphs to aid in the evaluation. It is easy to see that there is a certain degree of difference in the length of text of type ham and spam. The longer the text, the more likely it is of type spam. The same applies to website descriptions. which are usually not too long for SEO purposes. Instead, when our attention is focused on the number of punctuations, we can see that there is no effective distinction between the two types, so it is not considered as a part of the features. Likewise, the presence or absence of a web link is not sufficient as a reference. The number of numbers is an important indicator. The initial statistics even differentiated the length of the numbers, but in the end, we found that the text of the ham type basically does not contain numbers. However, in spam, more numbers are often used, so we use the number of numbers in the text as a feature, regardless of their length. It also fits our intuition that even a tool site that tends to list the number of partners or users it has can be considered a form of marketing. This part deals with the explainability of the model, rather than serving an explicit purpose. For example, optimizing for a specific function. Explainability is exploited to ensure that some real concerns are not negatively impacted. In a real production environment, if a model needs to be deployed online to provide a service, it is usually necessary to explain the model to celebrators, leaders, and regulators to ensure that the model is fair, transparent, reliable, and reasonable. Here, we use the feature importance values confusion matrix to try to justify that the previously introduced features work, and partial dependence plots to show how the model is affected by change in features after converging to a particular feature. The feature importance values and the confusion matrix are relatively easy to understand, and we can see that the length of text and the number of numbers do play an important role. Partial dependence plot, also PDP, is a useful tool for obtaining insights into the relationship between features and predictions. It helps us understand how different values of a particular feature impact models' predictions. The partial dependence plots shown in the two images on the right may not be very clear due to zooming. However, combined with the line representing the mean as the overall trend, we can see that as the length of the text increases, so does the likelihood that it is a spam type, but it is more balanced overall. And once there are numbers, the model is particularly inclined to judge the type of spam. But the number of numbers above the threshold does not bring big chance to the prediction. In this explainability stage, on the one hand, it is verified whether the features are reasonable and whether they can have a certain degree of influence on the model. On the other hand, it also gives some guidelines for model prediction, which helps to confirm the reasonability of the model. In this section, we will try to further optimize the model using hyperparameter tuning. In fact, with the use of NLP techniques and further engineering, the accuracy of models has increased from about 93% to 97%, and we usually consider 95% plus models to be usable. There are some simple ways to further improve accuracy. Machine learning algorithms typically contain a large number of parameters that can be used to train the model. In machine learning, hyperparameter optimization or tuning is the problem of choosing a set of optimal hyperparameters for a learning algorithm. A hyperparameter is a parameter whose value is used to control the learning process. We only consider the combination of two parameters here: the number of trees in the forest at the depth of its decision tree. So it is appropriate to use grid search. Grid search is the basic method of hyperparameter tuning. It performs an exhaustive search for the hyperparameters specified by the user. This method is the most direct and leads to the accurate predictions. Using this tuning method, the user can find the best combination. Grid search is applicable to several hyperparameters, but the search space is limited. By outputting the main classification matrix, we can compare the effects of different parameter combinations. We finally decided to use 50 and none and the final parameters, and the accuracy of the model advanced to the 99% range. Of course, the work here is crude, and we didn't do it with new techniques like transformers. Attention-based methods might be able to better recognize connections between contexts and provide more accurate detections. On the other hand, we also need to add methods that can explain word vector features, such as trying sharp and slim. In recent years, some transformer-based virtual attention methods can also do this. We just explained how the model works. Combined with the explanations from Yan Yiming and Zheng Zekai, you should have an overall understanding of our project, a search engine built from scratch that does some of the basic tasks of a modern search engine, such as keyword-based text search and content-based image retrieval. Also, we use machine learning models to improve user experience through spam detection. We also published a Jupyter Notebook using MkDocs to show our model design and implementation. The project is well organized, including code edited and continuous integration. I will show you some examples and give you a summary of the work. Of course, I'll also include some follow-up planning considerations. Let's see Marianne in action with some pictures. On the top left corner is Marianne's homepage, with a search box and a random picture. In the middle, and is the page where the users end their URL. After ending, it will start to crawl the web page. On the top right is an example search. Search for build to get some available results. On the bottom left is the page to upload images for search. The bottom right corner is the result of searching for an image. For the chi-square test, the smaller the score, the higher the similarity. Allow me to recap what Marianne is. Marianne is a search engine built from scratch with keyword-based text search, content-based image retrieval, machine learning model for spam detection. It seems a lot, but there is still a long way to go before a truly modern search engine. Although the course has ended and the development of Marianne has temporarily come to an end, there are still some interesting work that can be continued, which can be used as some directions for future research on search engine design and implementation. Vector search captures the meaning and context of unstructured data and is commonly used for text-on-image processing, enabling the use of semantics to find similar results and obtain more valid results than traditional keyword retrieval. Although the image retrieval method in Marianne is almost a vector search, but we can do better, and it may be a good idea to introduce a vector database. We can usually search image by keyword or by the context of the web page the image is in, and when we can hit the keyword, we can get better results. However, with the development of large models, we can use new techniques here, such as CLIP, which can obtain semantics from incoming texts and images and match them. An interesting example is that when typing two dogs playing in the snow, we can match the right image, not just based on the keywords dog or snow. Considering that search engines often need to face massive data retrieval, performance is also very important. How to adjust the algorithm to achieve both performance and effect, and how to expand from standalone to distributed are meaningful issues. We also need to consider how a measured, large-scale system can gradually evolve to provide truly valuable service to the public. Now you have got the gist of Marianne. Thanks.